In April 2026, something rare and precise is about to happen in the space around Earth, and the timing is no coincidence, because the universe doesn't traffic in coincidence. A comet's plasma tail will sweep through our orbital path. But not just any comet, and not just any tail. This one arrives during a sunspot maximum, during a high-speed solar wind stream, and during the aftershock cascade of a major earthquake. Three separate systems, all reaching peak intensity in the same 48-hour window. The comet is C2025 R3 PANSTARRS, a long-period visitor from the outer solar system on a trajectory that brings its invisible ionized tail directly across Earth's orbit around April 25th and 26th. That alignment alone is rare. Long-period comets swing past Earth only occasionally, and for their plasma tails to intersect our orbital path. Not just come near it, but pass through it. Happens maybe once per decade. This is one of those decades. But here's what makes April 2026 unprecedented. Three spacecraft are positioned and ready. ACE and DSCO-VR at the Sun-Earth boundary, monitoring the solar wind in real time, and Stereo A off to the side, watching the interaction unfold. For the first time in 30 years, we have instruments that can actually measure what happens when a comet's plasma tail meets Earth's magnetosphere. And we'll be able to do it not by accident, but by design. The last time this happened was in 1996. A spacecraft called Ulysses was in the middle of its mission, studying the sun when it flew directly through the tail of Hyakutake, one of the brightest comets of the 20th century. The scientists didn't plan it, Ulysses just happened to be there. And what it measured was so strange, so unexpected, that 3 decades later we still don't fully understand it. The plasma tail behaved in ways the models hadn't predicted. Questions opened up and stayed open, waiting for another chance to observe. We're getting that chance in April 2026. And it's arriving not in isolation, but embedded in a perfect storm, a convergence of 3 separate phenomena that almost never overlap. The sun is approaching solar maximum, the phase where sunspot activity peaks and flares become routine. A coronal mass ejection stream is heading toward Earth from a high-speed solar wind region, and Japan's seismic system, still reverberating from the magnitude 7.4 earthquake that struck on April 20th, will be in active aftershock mode. When the comet's tail arrives, it won't meet a quiet solar system. It will meet one in chaos. The question driving the next section is simple. Why does this convergence matter? What does it change about what we'll see? And what does a comet's invisible tail actually do when it crosses the boundary of a planet's magnetic shield? So that chaos matters because of what the comet itself is bringing to the collision. C2025 R3 PANSTARRS isn't a random visitor. It's a long-period comet, one that takes centuries to orbit the sun, and its path has already been calculated with enough precision to know exactly where its tail will be on April 25th. And that's where the alignment becomes extraordinary. A comet's plasma tail isn't a solid thing. It's an invisible stream of charged particles, ions and electrons stripped from the comet's nucleus by solar radiation and carried away by the solar wind, streaming outward like a flag made of electricity. That tail can stretch for millions of kilometers. But here's what makes this one rare: the geometry. Most comets' tails sweep past Earth at a distance, miss us entirely, or graze our orbit when Earth isn't there. The odds of a comet's tail actually crossing Earth's orbital path while Earth is nearby, within days, sometimes within hours, is small enough that it happens maybe once per decade, if that. 2025 R3 PANSTARRS is one of those once-per-decade events. Its trajectory isn't accidental. The comet has been traveling through space for decades before this encounter, following a path locked in by gravity, and that path is taking its plasma tail directly through the zone where Earth orbits. And Earth will be there. The last time this happened, the last time we knew for certain a comet's tail would come this close to us, was 1996, comet Hyakutake. And here's where the story gets strange. We weren't watching for it, not really, but a spacecraft called Ulysses, which was out there for an entirely different reason, studying the solar wind at high latitudes, happened to fly directly through Hyakutake's plasma tail. It was an accident, pure luck. And in that accident, Ulysses measured something that changed how we think about comets. It sent back data showing the tail had a structure, a complexity, that nobody expected. Magnetic fields wrapping around it, waves propagating through it, a depth of phenomenon packed into what we'd assumed was just a thin stream of particles. And then the spacecraft moved on, and we didn't see another comet's tail up close again. 30 years passed, we built better instruments, we learned more about the solar wind, we deepened the questions, but we never got another direct measurement, until now. The difference between 1996 and 2026 is that this time we're ready. We know the comet is coming. We know when. We know where its tail will be, and we have 3 spacecraft positioned across the solar wind observation network: ACE, near the Sun-Earth point, Disco VR in the same region, and Stereo A, far off to the side, all of them equipped with magnetometers, plasma sensors, and particle detectors that Ulysses didn't have. This isn't an accident. It's the measurement we've been waiting 3 decades to make. But here's what makes 1996 the real ghost story in this timeline. The Ulysses spacecraft wasn't built to study comets. It was built to study the sun. Launched in 1990 to orbit over the solar poles and measure the sun's magnetic field and the solar wind flowing out from it. Its path through the inner solar system was fixed years before anyone knew Hyakutake was coming. So when that comet rounded the sun in April 1996, when its plasma tail stretched across the solar system like a banner millions of kilometers long, Ulysses just happened to be in the way. The spacecraft flew straight through it, and for the first time in human history, we had direct, real-time measurements of what happens when a comet's tail collides with a planet's magnetosphere. What the instruments found was supposed to be simple. A comet's tail is made of ionized gas, plasma, torn from the nucleus by solar radiation and solar wind pressure. It should be a thin stream, relatively uniform, following a predictable path. Instead, Ulysses detected something chaotic. The plasma was clumpy, the magnetic field was twisted. There were sudden spikes in particle density that couldn't be explained by the models we had. A physicist looking at the data would see a clean, understandable phenomenon. But the phenomenon wasn't clean. And then Ulysses was gone. It kept flying, kept sending back data from the sun, and comets faded from its mission. We had one measurement, 30 years ago, and it raised more questions than it answered. Every comet expert on Earth has spent those 3 decades with the same frustration. We had one chance, one glimpse, and it left us confused. We didn't even have the right instruments on Ulysses. It wasn't designed for this, so it wasn't optimized for this. We were like a photographer who accidentally captures the only picture of an extinct animal and realizes too late that the camera's lens was smudged. That's the precedent we're walking into in 2026. This isn't a happy story where we learned everything from 1996 and moved on. It's a 30-year-old scientific debt. Every researcher who studied comet physics in the last 3 decades has been stuck in the same place. One measurement, one mystery, and the knowledge that we might never see another comet's tail at Earth orbit distances in our lifetime. Comets on that kind of trajectory don't come often. The alignment has to be perfect, the timing has to line up, and when it does, you get maybe a day or 2 before the tail drifts past and you lose the chance for another generation. April 2026 is that second chance. 30 years later, with instruments designed for exactly this kind of measurement, positioned where we need them to be, all watching the same moment. If we see the same chaos Ulysses saw, we finally get to ask why. If we see something different, we get to revise everything we think we know about how plasma tails behave near planets. Either way, we're not blind anymore. This isn't an accident. We're ready. But here's where the story turns. We're not just getting a second chance at a comet, we're getting that chance in the worst possible moment the solar system could have chosen. On April 25th, 2026, when the plasma tail crosses our orbit, the sun is going to be in the middle of its 11-year cycle peak. Not just active, at the exact moment when a sunspot region directly facing Earth will be at maximum flare productivity. This isn't a minor detail. Solar flares eject billions of tons of plasma outward at 1,000,000 miles per hour. They create shockwaves in the solar wind. They reshape the magnetic field between the sun and Earth, and they're going to be happening the same 48 hours the comet's tail arrives. On top of that, a high-speed coronal hole stream, a river of solar wind already moving faster than normal, will be flowing past Earth at the exact same time. The sun's magnetic field, corrupted by flares and accelerated by the stream, will be chaotic, turbulent, unpredictable, which is precisely what makes it valuable for science and precisely what makes it dangerous for assumptions. And then there's the earthquake. On April 20th, 2026, 5 days before the comet arrives, Japan experienced a magnitude 7.4 earthquake. That's not a prediction, that's in the historical record now. The aftershock sequence from that event will still be unfolding when the comet's tail crosses our orbit. Thousands of small tremors, the Earth's crust still adjusting, stress fields still redistributing, seismographs around the world will be ringing. So we have a rare comet whose plasma tail we've only measured once by accident. A solar maximum with flare-productive sunspots aimed directly at Earth. An accelerated solar wind stream, and a major earthquake's aftershock sequence, all coinciding in a 48-hour window. This isn't chaos for its own sake. It's a rare collision of systems that almost never overlap. And it changes what the measurement means. If the comet's tail behaves normally, if the plasma stays coherent, if the particles flow the way they did in 1996, then we know something about how plasma tails are robust. But if the comet gets shredded, if the solar wind tears it apart, if the flare hits at the exact moment of closest approach and we see something totally different from Hyakutake, then we learn that the context matters more than we thought, that a comet's tail is fragile, that the same tail might look completely different depending on what the sun decides to do on any given day. This is why the instruments are positioned where they are. AC, Desco VR, and Stereo A aren't just watching the comet. They're watching the entire system. The sun, the solar wind, the magnetosphere, the particles flowing between them. They'll catch the moment the comet enters that chaos and see what it does. ACE sits at the L1 point, a gravity balance point between Earth and the sun, about 1 million kilometers sunward. It's been there since 1997, positioned like an early warning buoy, catching the solar wind before it hits us. Desco VR is at the same L1 point, but it arrived later, in 2015, and it carries different instruments: magnetometer, particle detectors, spectrometers that can break apart the solar wind into its atomic signatures. And Stereo A, the Solar and Terrestrial Relations Observatory, is off to the side, trailing Earth's orbit, which means it sees the comet and the incoming solar wind from a different angle than we do from the ground. 3 vantage points. 3 sets of instruments. None of them can see the comet directly the way a telescope can. They don't need to. What they're measuring is invisible. They're measuring the collision itself. Here's what happens in the 48 hours around April 25th. The comet's tail, a river of plasma, ions, electrons carrying the comet's gases pushed outward by the solar wind, enters the space around Earth where our magnetosphere begins to grip. ACE catches the solar wind's properties in real time: its density, its speed, its magnetic field. As the tail gets closer, Desco VR measures the moment Earth's magnetic field starts to react. It's like putting your hand into a stream and feeling the current change as you move into the flow. And Stereo A, from its offset position, watches the same moment from the side. It sees the geometry, how the tail is oriented, whether it's wrapping around Earth's magnetosphere or getting shredded, whether the particles are flowing in the direction we expect or scattering in directions they shouldn't. The data streams back in real time, not video, numbers, thousands of measurements per second from each spacecraft, densities in particles per cubic centimeter, speeds in kilometers per second, magnetic field strengths in nanoteslas, temperature, composition, direction. For the first time in 30 years, we'll have a complete record of what happens when a comet's plasma tail moves through Earth's neighborhood, not reconstructed from a single probe stumbling into it by accident, but measured from 3 different angles simultaneously, with instruments designed for exactly this kind of work. And if the solar flare hits, if the sunspot region erupts at the exact moment the tail is closest, if the high-speed coronal hole stream crashes into both the comet and Earth's magnetosphere at the same time, then we'll see something we've never seen before. A planetary magnetic field caught between a comet's tail and the full fury of the sun, measured in real time by instruments waiting for this exact moment. Now here's where the story splits. The science is extraordinary, the timing is real, but the apocalypse narrative spreading across social media right now is not. Start with what we know will happen. A comet's plasma tail will reach Earth's orbit, solar activity will be elevated, the magnetic field will feel it. That part is physics, not speculation. But somewhere between the data and the viral videos, the interpretation changed. People started asking, what if the comet's tail destabilizes Earth's magnetosphere? What if it triggers earthquakes? What if the solar activity amplifies it into something catastrophic? The answer is, we don't know. And that's exactly why this is worth watching. Not because we're afraid of it, but because the uncertainty is scientific, not doomsday. A comet's plasma tail is thin, extraordinarily thin. It's a stream of ionized gas so diffuse that if you flew through it, your instruments would detect it and you'd feel nothing. Earth's magnetosphere is a magnetic bubble. It's not fragile. It's been hit by solar wind constantly for 4.5 billion years. The idea that a comet's tail could break it fundamentally misunderstands what both things are. But here's what we genuinely don't know. How does Earth's magnetosphere respond when a comet's plasma tail, moving at 40 kilometers per second, carrying its own embedded magnetic field, intersects with it at the exact moment a coronal hole stream is already compressing it? That's not a doomsday question. That's a plasma physics question. And we have never measured it before. As for earthquakes, Japan's aftershock sequence and the comet's arrival are a coincidence, not a causal chain. Earthquake triggering from electromagnetic effects is a hypothesis with no solid evidence, not a mechanism. The M7.4 in April was a tectonic event driven by plate tectonics, not magnetospheric activity. The aftershocks follow the aftershock laws we understand. The comet doesn't change that. What actually matters is this. We are about to collect data on a plasma magnetosphere interaction during peak solar activity that we have never intentionally measured before. The last spacecraft to see a comet's tail at Earth orbit didn't know it was coming. Ulysses stumbled through Hyakutake's tail and sent back numbers that still confuse us. This time we are ready. 3 spacecraft positioned, instruments calibrated, 3 decades of technological improvement between then and now. And a 48-hour window in April when we might finally understand what happens when a comet crosses our path during a solar storm. The science doesn't need doomsday to be worth paying attention to. The extraordinary is enough. So here's what happens on April 25th and 26th, 2026. For 48 hours, the plasma tail arrives. ACE sees it first, the solar wind satellite picks up the density shift, the magnetic field twisting, maybe a jolt in the particles streaming past. Then, DESCO VR catches it, stationed 1 million kilometers out, watching the boundary between the solar wind and Earth's magnetosphere in real time. And Stereo A, off to the side, watching the geometry, the angle at which the tail sweeps in, how wide it spreads, what shape it holds. None of this is invisible. The instruments don't just detect it, they measure it. Every particle density, every magnetic field vector, every energy spectrum. That's the difference between seeing a comet's tail and understanding what a comet's tail is. The data streams down to teams who've waited 3 decades for this. But here's what makes it genuinely hard to predict: the overlap. The comet's tail doesn't arrive alone. It arrives into an active magnetosphere. Earth's magnetic shield is already reacting to the solar storm, already buffeted by the coronal hole stream, the flares from that productive sunspot region still firing. So the instruments won't just see the comet's tail, they'll see what happens when a comet's tail, a thing made of ionized gases stretched across millions of kilometers, collides with a magnetosphere that's already been hit once, is bracing for hit after hit, and is trying to hold Earth safe underneath. That's the actual science, not doomsday, not a concern. Data, the kind you can't get any other way, from any other event. 30 years of waiting, 48 hours of measurement, and after those 2 days, the tail sweeps past, and the magnetosphere settles, and the data becomes the most complete picture we have of how a planet and a comet can touch. You'll probably see nothing. Most of the Earth sees nothing. No lights in the sky, no rumble, no sign at all that something extraordinary is happening in the fields above you. But somewhere, in quiet labs, the instruments will be running. And for the first time since Ulysses stumbled into Hyakutake's tail by accident, someone will know what a comet actually does when it reaches us.